Okay. Hello, everyone, and welcome to this fifth episode of a second season of O-MESS seminars. Today we have two talks. The first one is given by Vedan Chandra from the Harvard-Smithsonian, and the second one from Thais Pacheco from the University of Sao Paulo. So Vedant can start sharing the screen, and he will talk about his work on circumstellar material and rotation in runaway supernova survivors.
Thank you so much. Is my screen visible, and can everyone hear me?
Yes, it is visible, yes.
Perfect. Thank you so much. It's really a privilege to be able to talk to you all today. Thank you for taking the time. I wanted to talk to you about a really interesting star that I've been studying for over a year now with a fantastic team of collaborators who I'll list at the end. This was mostly work I did as an undergraduate at Johns Hopkins. I've now moved on to graduate school at Harvard. And I want to talk to you today about our detection of circumstellar material and rotation in a runaway supernova type 1a donor. So to start off with, I wanted to give quite a bit of background on what it is we're talking about here and where the star comes from, or where we think it comes from. So as we all know, we all in this room probably love and adore type 1a supernovae because of their various uses, for example, as cosmological standard candles. However, for many decades now, it's been quite uncertain what the exact progenitor scenario is for these supernovae. It's pretty well accepted that what actually explodes is a white dwarf, but the nature of the unseen companion is more uncertain, and it's been the matter of a lot of debate. One possible scenario that's been developed by Ken Shen and his collaborators is the so-called D6 scenario, which stands for dynamically driven, double degenerate, double detonation. And in this picture, you have a double degenerate scenario where you have two white dwarfs that in spiral due to the emission of gravitational waves until dynamical mass transfer begins. And in this picture, you can imagine that once the primary accretes enough helium, that helium could trigger a double detonation, where the helium detonates, which subsequently detonates the carbon in the core, unbinding the star and causing the type 1a supernova. And so this is a theoretical model for type 1as that makes a possible observational prediction, which is that that donor that gave the helium to the primary, it could actually survive the explosion if the explosion happens early on enough in the dynamical mass transfer. And in that situation, you'd expect this donor to be slingshotted out of the binary and be hurled out at essentially its orbital velocity at the time of the explosion in excess of thousands of kilometers per second. And so Ken and his collaborators kind of thought about this prediction and then went looking in this beautiful data set from the second data release of Gaia to look for such unbound hypervelocity stars. And they found three. And you can see here on the right-hand side, I'm showing two plots of the three stars that Ken found in his paper. On the top, you can see their total galactocentric velocities. They're all in excess of 1,000 kilometers per second. These are among the fastest stars in the entire Gaia data set. And in the bottom, you can see these stars on the color magnitude diagram. And you can note that, first of all, they cluster on the CMD, suggesting that they're in a similar evolutionary state. And also the fact that they lie above the cooling track for canonical white dwarfs. And so these stars are clearly inflated by about an order of magnitude compared to typical white dwarfs. And we'll talk a little bit more about why that might be. In Ken's paper, he also took a low resolution spectra of all three of these objects and found that they look remarkably similar, again, tying them to a common evolutionary origin. Now, the star we focus on in our paper, and the one that kind of piqued our interest, is D62 in Ken's paper. Its official telephone number is LP3989. D62 is particularly interesting because, as Ken showed in his paper, and as you can see on the top right panel here, if you take D62's orbital trajectory and simply extrapolate it backwards in time by about 10 to the 5 years, you land near the center of a known supernova remnant. And so that's a pretty interesting thing that, again, ties D62 to this supernova progenitor scenario. What initially made us interested in this star, and I come to the first plot from our paper, is the bottom right panel. where you can see the spectral energy distribution of D62 from various observatories. In red is the observations, and in blue is the stellar model. And you can clearly see that there's these two data points from the Y-space observatory that simply don't match up with the stellar model. They're way too high. And so there's this detection of a very strong infrared excess around D62. And that's what made us want to study this object in a little more detail. As you can see, we can fit this infrared excess with a pretty simple black body model that tells us that it has a temperature of about 700 Kelvin, and it appears to be quite puffy. It appears to be much more extended than the radius of the star by a couple of orders of magnitude. And so that's just one way to interpret an infrared excess like this, is some kind of puffy shell of dust. And that's what we fitted over here. And so we wanted to dig into this a little bit further. And so we went out and got a slightly better spectrum of D62 from the Apache Point Observatory. And I want to stress here that we haven't done a very detailed abundance or atmospheric analysis of the spectrum. It would be fantastic for someone to get a higher resolution spectrum of D62 and perform a more careful abundance analysis to really figure out what's going in its atmosphere. But regardless, with the spectrum that we had, this spectral analysis was led by Simon Blouin, and he really found and made a very interesting conclusion from the spectrum. So what you can see here in black is our observation. And what we overlay with the colored curves are very simple kind of single species models for carbon and oxygen, just to give you an idea of what those lines should look like. I want to direct your attention to the top panel and the red line, which is a carbon model at some given abundance of carbon. And what you'll see is that the red model has these strong bands, which are the so-called C2 Swan molecular bands. And you can essentially see that at this present level of carbon that we have in this model, we're already essentially pushing the limit of how much carbon we can fit into this photosphere. Because if we were to add any more carbon, it would make those bands much stronger. And we simply don't see such strong bands in our observed spectrum. And so we're really pushing how much carbon we can fit into this model. However, if you look at the bottom panel, which is the red part of the spectrum, I've highlighted with some red arrows very strong atomic lines of carbon that we see in our observed spectrum, but that at this carbon abundance simply aren't present in the photospheric model. And so one possible conclusion from this that Simon and I have been discussing is that this additional absorption, this additional atomic absorption of carbon has to be coming from some place that isn't the photosphere. It has to be coming from a place where the pressures and densities are such that you can produce this atomic absorption without the issue of having those really strong molecular swan bands. And so in our paper, we kind of tie this together with the infrared excess to suggest that there's this shell of circumstellar dust that appears to have carbon in it. And we think the most plausible explanation for this is that it's simply inflated layers from the star itself. We discussed earlier how these stars are currently in an inflated state. And so it's reasonable to expect that at some point soon after the supernova, they were inflated by quite a lot, and they are perhaps now shrinking back down. And some of those outer layers could detach and present as this dusty circumstellar material that we see now. That's just one possible picture, and that's the one that we put forward in the paper. So in addition to this circumstellar material, the second main observation that we made about D62 is what we think is a signature of surface rotation. And this was quite a serendipitous discovery. We were in fact ready to submit the paper. And then one of our collaborators, Boris Gansiker, he just sent us an email saying, I think I see something in the light curve of this object from this Wiki transient facility. And it was this hint of periodicity. And so we went out and got more data on the star. We got photometry from the Liverpool telescope. And Ken and his collaborators also took a Hubble Space Telescope STIS spectrum of D62. And what's really cool about STIS is that it actually tags and time tags the photons that hit the detector as they hit the detector. And so you can take this kind of 8-hour integration of the spectrum that Ken and his collaborators collected and bin it up in time to produce an ultraviolet light curve, which is what you can see in blue at the top here. And so what you see in this figure is all these photometric data sets of D62 folded to a period of about 15.5 hours. And you see this very clear sinusoidal trend in all of the data sets. And here I want to stress that that HST data set really isn't phase folded per se. It's a continuous 8-hour monitoring that shows this trend. And that really kind of makes us confident that this trend is real and this variation is real. So there's a lot of possible explanations for sinusoidal variation in a star's brightness. The one that we put forward in the paper that we think is the most plausible is that it's some kind of rotationally modulated signal, where you have some kind of brightness variation on the star that rotates in and out of view at the rotational period of the star. In terms of the origin of that brightness variation, we're really not sure. It could be something like a spot, and that really warrants more study. One possibility, of course, is that D62 really has had front row seats to one of the most violent events that happens in the universe, a type 1a supernova. And so it's somewhat reasonable to expect that some of the ejecta from the supernova, for example, could have been asymmetrically deposited onto D62. Now, it's a very open question about whether any of those inhomogeneities would survive to the present day. But if they do, you could certainly imagine them presenting as some kind of inhomogeneity in the surface brightness, either due to differences in line blanketing or opacity. And that could produce the rotationally modulated variation that we see right now. Another kind of cute connection between the observed rotation rate of D62 and the D6 scenario was pointed out by another one of our collaborators, Evan Bauer. And it follows from a very simple kind of undergraduate level conservation of angular momentum. And the idea here is that in the final throes of the D6 binary, when these two binaries were orbiting around each other, the orbital period would have been on the order of minutes. There's still a lot of active work going on this, but it's reasonable to expect that that binary would have been tidally synchronized to a pretty high degree, in which case D62 would have essentially been rotating at a period of on the order of a few minutes when its companion exploded. Now, like I said, D62 is now inflated by about a factor of 10 compared to what typical white dwarfs are. And so that factor of 10 increase in the radius, if you just assume simple conservation of angular momentum, would very handily take you from a rotation period on the order of a few minutes to on the order of tens of hours, which is what we see right now. So, of course, there's a lot of complications here about whether D62 fully conserved its angular momentum, would there have been mass loss and things like that. But it's just a kind of cute order of magnitude connection between the D6 scenario and what we see presently in D62. And so this kind of summarizes our detection of this, what we think is surface rotation. And I'm definitely open if anyone else has a different idea. And so in our paper, we present two interesting new things about this fascinating object, D62, which we argue point to D62 truly being a runaway supernova donor from this D6 scenario. As it is with all observations, we would love more data. And in particular, we love more optical spectroscopy, as I mentioned earlier, to really drill down on the abundance analysis of the chemicals that are in D62's atmosphere and where they come from. And also to kind of pick apart what part of the absorption is coming from the photosphere and what part of the absorption is coming from the circumstellar material. That would be really interesting to see. It would also be interesting to see infrared spectroscopy of this system, for example, with the James Webb Space Telescope, because we want to figure out what that circumstellar material is really composed of. Is it consistent with some kind of carbon-rich material that was inflated from the star? Does it potentially have signatures from the supernova itself, perhaps in the form of deposited ejecta? Those are the kind of questions that we could really answer with infrared spectroscopy. In addition to the observations, I think there's a lot of really interesting work to be done with these objects on the theory side to really understand how they evolve after their companions explode. I mentioned the fact that these D6 objects are inflated by a factor of 10 compared to regular white dwarfs. I think it's a totally open question about how that actually happens. Why are they inflated? And there's a lot of possible pictures that people have proposed, and I'd really love to see a resolution to that issue. On a related point, we have this question of timescales. We find these 3 D6 objects kind of clustered on the color magnitude diagram right now. Does that mean they've kind of paused in an evolutionary state? What does that evolutionary track actually look like as a function of time as they go from that inflation post the companion supernova to where they are, where we see them today? And then finally, what we expect is that they would shrink down and cool back down to the white dwarf cooling track. it would be fantastic to have a better idea of what that evolutionary track actually looks like. And then finally, of course, this D6 scenario seems pretty cute. It seems to produce these runaway donors. Does it actually reproduce the properties of observed type 1a supernovae? That's another open question. And in fact, this is something that Ken's been working on a lot. And I would direct you to some papers he's written this year that dig into this question a little bit more. And so that's essentially what I wanted to talk to you about. At this point, I would love to take questions from everyone. And once again, I'd like to thank you for your time. It really was a privilege to be able to present this to you. Thank you.
Thank you, Vedant. Very nice summary. Do we have questions from anyone? Okay, I can see 6 raised hands. Oh no, someone clapping. Sorry. You can write questions, yes, in the chat or ask them yourself. So there is a question from Stephen Parson. He says, doesn't the strength of those lines imply that the circumstellar material contributes quite a lot to the optical flux? Could this be the origin of the photometric variability?
That's an interesting question. So we thought a little bit about how the photometric variability could come from what's orbiting the star. And the main thing that kind of made us hesitate there is to see that variability, we think that you need to have some kind of inhomogeneity in what's orbiting the star. And we had some just quick discussions where we thought that we would assume that that would kind of become more homogeneous and wouldn't show variations. But I think that's a completely reasonable point. And that's kind of, again, why I would love to piece apart a little bit more about how much of the absorption is coming from the photosphere and how much is coming from the circumstellar material. Because I agree with you. I think it is actually possible that it could be coming from the circumstellar material. That's a great point.
And there is also a question related to this variability from Jiri Krichka. Why there is a phase shift between UV and optical light curves?
That's a fantastic point, and I can actually go back to that figure here. This is something that we saw, and we were a little bit confused about exactly why this was happening. But we explained this a little bit more in our paper. We think the origin of this phase shift is that it's not real. We think that it's mainly due to some kind of systematic uncertainty in the exact orbital period. Due to kind of the mixed nature of these data sets, the random sampling of the ZTF and the Liverpool light curve, for example, the exact periods that you get from these 3 different data sets varies a little bit, and there's a lot of fine structure aliasing. And so if you change your assumed period by as little as I think about 0.5%, the phase shift either disappears or shifts to something different. And so with a little bit more photometry, I think we'd be able to accurately drill down the period of this object a little bit better to under 0.1% or something like that. But yes, we think the phase shift, at least this large phase shift that you see here, probably isn't real. It's probably just some kind of systematic uncertainty in the period.
Good. Still, since we have still time, there are 2 more questions. One from Alexei Brobrik, who says, on angular momentum conservation, can we say something about how little the donor star was stripped during the explosion?
That's a good point. I think that's definitely important. I'm not sure if we would be able to get that constraint from the angular momentum conservation, because the angular momentum conservation is the biggest assumption that we're making here. Certainly, if it was stripped, that would affect this assumption a lot. And so the question becomes, how well can we constrain its present day mass? And there's actually a really interesting paper on the archive by Evan Bauer about kind of what the present day runaway velocities tell us about the masses of these donors at the time of the explosion. I think a little more spectroscopic analysis of these stars to get their surface gravities and things like that would be interesting. But yes, I think that if it was significantly stripped, that would definitely affect the assumption of conservation angular momentum. Certainly it was stripped a little bit because we see this circumstellar material, but I will stress that the implied mass of the circumstellar material we see is extremely low. It's not a significant fraction of the stellar mass.
Okay, and the other question from Mukramin Kilic, this regards the other two D6 stars, and he's asking whether they also show fast rotation, infrared excess, or circumstellar carbon.
That's a fantastic point, and that's definitely something that we tried to discuss in our paper, which is that what makes D6.2 special compared to the other two. What I'm showing on the right here is just another plot that shows on the bottom right in particular, the WISE1 minus WISE2 color for a sample of random stars, and then the red star is D6.2, and the blue dot is D6.1, another one of the D6 stars. D6.3, unfortunately, is in a very crowded field, so its WISE photometry is uncertain. It's actually an open challenge for someone to maybe see if they can do some fancy PSF fitting and get a value. But certainly based on this, it seems that D6.1 doesn't seem to have that much of an infrared excess. In terms of rapid rotation, I would love to see more photometric follow-up of those. I think JJ, one of our collaborators, looked at the test light curves for these objects. They're a little bit faint for tests, but there doesn't seem to be a lot of variation. That said, the variation that we see in D6.2 is pretty small. It's on the order of a few percent. So I think they should be monitored a little bit more, because if they are in a similar evolutionary state, then we would like to see these signatures in those stars too. What we discussed in our paper is that it's also possible that they aren't so much similar in terms of how long it's been from the time of their supernova. D6.2 could perhaps be the most recent one, which is kind of supported by the fact that it's the only one that has the supernova remnant. But if it is indeed the most recent one, then maybe these observations that we see are transient, and then either the surface inhomogeneity homogenizes enough that you don't see the rotational signal, or the circumstellar material slowly is lost from the system. And so that would be one possible way in which it's the only one in which we see these observations. But I completely agree. I'd love to see more observations of both the D6 or both the other D6 stars.
Okay, we have a few more questions, but I would suggest we discuss them in the, actually we have a couple of minutes more, so maybe we can ask them here. So there is Marcelo, but we'll skip him because he's an organizer. And the other one is anonymous, might be Tom Marsh from the acronym of the Warwick system, or Boris. The idea, so he's asking if there is any idea of the current evolutionary timescale, wondering whether there is a hope of seeing spin up.
That's a really interesting point about whether, as the star contracts, would you start seeing it spin up? I'm not entirely sure. I think the one calculation we did was the Kelvin-Helmholtz time system is on the order of millions of years. But I think it's an interesting thing to test. I would, like I said, love to get a very secure measurement of the period right now with more photometry, and then maybe look at it again in 10 years and see if we do see some kind of signature that's spin up. That would be, I think, probably one of the best ways to measure the changing rotation rate of this system. That's a really interesting question, yeah.
Okay, and finally we have a question from Gajik Tovmasian. Shouldn't the circumstellar matter produce some kind of bow shock in such a high velocity runaway star?
That's an interesting point. So you mean just from its interaction, I'm assuming from its interaction with the interstellar material? That's an interesting point. This is actually a little calculation we ran. And I think the conclusion we arrived at was that it's dense enough that you wouldn't expect the interstellar material to kind of blow much of it away. But I haven't looked into that in that much detail. That's an interesting point.
Okay, thank you very much, Vedant. And I think we can move on with the next speaker, Thaisa.
Thank you so much.
And of course, if anyone else